When we began learning statistical methods for analyzing data for our research studies, we focused on parametric statistical methods, yet probably without using that term. In fact, many researchers will spend their entire career within the realm of parametric methods, and there's really no need to define what that means because that's all they're going to do. For such users, it's simply using statistics. But for those who take a journey into the world of nonparametric methods, as we're going to do, it's going to make sense to distinguish what is meant by parametric and what is meant by nonparametric. We're going to begin our journey by defining parametric methods, so later we can contrast it with nonparametric methods. It will be easier to understand what nonparametric methods are if we know what we mean by parametric methods. The term parametric statistics refers to statistical methods based on known probability distributions. Now, probability distributions are mathematical functions, and those functions relate a potential observation as the input to the probability of observing that outcome as an output. The specific form of a probability distribution depends on one or more parameters, thus the term parametric. For example, the uniform distribution is a distribution for which the probability of making an observation that is within a certain distance of a specific value is the same within the entire range of that distribution, but zero everywhere else. Now, there are two parameters that specify a uniform distribution: the minimum and the maximum. So look at these two uniform distributions. These are two examples. The red distribution is a uniform distribution with two parameters, the minimum 1, the maximum 6. If you get below 1 or above 6, you will not observe anything. So the probability of observations outside of the range of 1 to 6 is 0. But within the range of 1 to 6, if we were to take an interval, say 1 unit wide, so from 1 to 2, there's a probability of observing values from 1 to 2. And that probability is going to be 20%. How did I know that? Well, I'm looking at 1 to 2 on the x-axis, which gives me my possible values or scores, and I'm looking at what we call the density on the y-axis. And the density is 0.2 all the way along from 1 to 6, which is what makes this a uniform distribution. If I multiply an interval of size 1 times 0.2, that gives me 1 times 0.2 equals 0.2, or 20%. So there's a 20% chance of finding a value between 1 and 2. Similarly, between 2 and 3, 20%. Between 3 and 4, 20%. This is a uniform distribution. If I take the entire range from 1 to 6, that's 5 units. And 5 times 0.2 is 1, or 100%. Makes sense, doesn't it? 100% of our values are between 1 and 6. This blue distribution has a minimum of 4 and a maximum of 12. It is still a uniform distribution, but it is a different uniform distribution. And notice that the probability density stays at 0.125 all along the range from 4 to 12. If you take 4 to 12, that's 8 units. Multiply it by 1.25. Again, you get 1, or 100%. We call the vertical axis density rather than probability, because if we called it probability, that would imply that I could take any single value with infinite precision, and that would be the probability. So I could say 2.00000 has a probability of 0.2. 1.5000000 has a probability of 0.2. That's not going to work because we have an infinite number of possible numbers between 1 and 6. And if you multiply all those by 0.2 and get 20%, you're going to be way over 100%. So the probability of a value with infinite precision is actually 0, which is why we have to have a range and multiply that range by the density in order to get probability. So this is a probability density function. Now, when we do research studies, we collect data. Data we collect during research studies are samples obtained from a larger unknown set of data that could theoretically, but not practically, be obtained from observing every member of our target population. If we then look for a function that seems to approximate the data that we're looking at, we might be able to find something like we have here with this uniform probability distribution function or probability distribution that matches nicely with what we see in this histogram from the data we collected. Now notice that the shape of data distributions do not strictly adhere to a mathematical model, but good mathematical models are reasonable approximations of reality. If we choose to use a mathematical model, we are saying this is close enough to the population distribution for the purposes of our study. So here we say our data are from a uniform distribution. We mean the uniform probability model will fit well with the data. Now, an important point that I will make repeatedly is that this mathematical model is a model of our population data, and we're looking at sample data. We're not ever going to have the population data. So we're making a guess from the sample data what the population data might look like. We might have theoretical reasons to believe that the population distribution will look a certain way. But whatever the case, when we create that mathematical model is for the population, not as we see pictured here for the sample. We're only doing it this way because we don't have access to the whole population. Now, there's something to be said about knowing that a probability distribution is a very good model of our population data. If we know what probability distribution will be the best model of a population distribution, and if we know that this is going to be an excellent model, not only is it the best model, but it's a really good model of our population distribution, then we can find or develop the most powerful method possible for making inferences to the population from sample observations. In other words, if we have a mathematical probability distribution that matches very nicely with our population distribution, the parametric procedure is going to be the best one. And in fact, a specific parametric procedure is going to be the most powerful statistical method. But that gets a lot of people in trouble because they forget these ifs. If we know the probability distribution is the best model and which one is the best model, and if we know not only is it the best model, but it's a really, really good model, then parametric procedures will be the most powerful. But if you think about how many times you work in research and you really don't know what the population distribution looks like, that gives you a hint as to why we may want to move from a parametric procedure to a non-parametric procedure. In practice, the vast majority of parametric statistical methods use the normal distribution as the probability distribution model for our population data. There are several reasons why this is the case. Some natural data can be modeled nicely with a normal distribution. For example, consider the length of mammal babies at birth. Take any mammal, look at the babies at birth, and look at the length of those. There is going to be a common length for these babies that is going to occur with great frequency. But as you get shorter and shorter, it's going to have less and less frequency. And conversely, if you get longer and longer, it's going to have less frequency. Think about the heights of 8-year-old girls. There's going to be some middle, some average in which many girls are close to that height. But as you get shorter and shorter, there's fewer of them. As you get taller and taller, there's fewer of them. Second, psychometric tests are purposefully developed so that they can be modeled with a normal distribution. So while many things naturally occur with a normal distribution, some man-made things purposefully have a normal distribution. IQ test. The SAT is created on purpose to have a normal distribution. It's calibrated so that the distribution will be that mathematical probability distribution that we call a normal distribution. Yet far and away the most important reason the normal distribution is used as a model is because of the central limit theorem. The central limit theorem states that a linear combination of random variables will asymptotically follow a normal distribution, and it's a theorem that's been proved. So what does that mean? A linear combination means adding things up. Take the mean. How do we find the mean? We add up a number of our observations, we divide by how many that we add it together, and we have the mean. So the mean is a linear combination, so the central limit theorem states that the mean will asymptotically, that means as you get more and more observations, it will approach a normal distribution. Now, if you have only a few observations, it may not be near a normal distribution, but if you have many, then it will be. The parameters of the normal distribution are the mean and standard deviation. So anytime we use statistical methods based upon the normal distribution, which is a mathematical distribution with parameters, 2 of them, just like the uniform distribution, but 2 different kinds of parameters, the mean and standard deviation. If we are using statistical methods based on the normal distribution, we are using parametric methods. This allows us to make inferences based on these parametric methods. That is, parametric inference is conditionally based on knowing the probability distribution that serves as a reasonable model for our data. Statistical methods based on the normal distribution usually focus on the mean, which happens to be one of the parameters of the normal distribution. In fact, the theoretical foundations of a hypothesis test that you learned in your first statistics courses, or a confidence interval for, say, the mean, is based on hypothesizing the parameter of the normal distribution, the mean, and then determining whether our data are consistent with that specific normal distribution, or whether we must reject that hypothesis because the data simply do not fit well with that model. The central limit theorem is about linear combinations such as the mean. So it's not about the original data distribution, but rather about the sampling distribution of the mean. So even though we can do valid parametric inference for the mean with the normal distribution, the central limit theorem does not guarantee this is going to be the most powerful method, because remember, in order to guarantee you have the most powerful method, your original data distribution for your population must adhere to some mathematical model, some probability distribution that has parameters. Inference also depends on other conditions, such as independence of observation, homogeneity of variance, homoscedasticity, random processes such as random sampling and random assignment. So in sum, we started through this video with the question, what are parametric statistics? What are parametric statistical methods or parametric methods? Answer, those are methods that are based upon probability distributions that we believe match well with the population data. If they do not, we're going down the wrong path. So you are in this class to discover, what can I do if I'm not sure if a probability distribution is a good representation of our population data? I'm looking forward to us making that exploration together.